before we go through those, yeah, let's do that. I just want to do a real quick kind of primer review. What does 8 mean?
Like higher on the oxygen, like more oxygen, like 3 plus.
Okay, 3 plus?
No,
4
4 plus.
plus. So it means 4 oxygens. What's the name of NO3 minus? Not you, unfortunately. It is nitrate. That should cause a problem because you just told me that 8 meant 4 plus oxygens. And yet I go to nitrate that has 3 oxygens. Your initial description of it was 100% correct. 8 means more oxygens. More oxygens than what? Than ite. What does ite mean? Less oxygens. Less oxygens than what? Okay. Then 8. You just hit a cyclic system of definition that's not going to work very well. Okay. And herein lies the big issue. When you go through and look at both the internet and your textbook, they'll go through and say 8 means more oxygens. Okay. Again, context is really important. More than what? 8 means more oxygens for that compound. When I look at the oxygen compounds with nitrogen that form ions, I have NO3 minus 2 and NO2 minus. Because I know that there are these two states, key word there, I knew there were those two states. I know that the one with fewer oxygens must be nitrite. And the one with more oxygens must be nitrate. Okay? I had to know all of that frickin' information. So instead of telling you 8 means more oxygens, how about we just say NO3 minus is nitrate? Because if you start going through and saying 8 means more oxygens, you're going to start to run into this trap of more oxygens than what? And what you're going to fall back on are what you see very commonly. And what you will see very commonly might be something like SO4 minus 2. Okay? So you see the 4, and that one's now sulfate. And you go, great, 4 means 8. So what's ClO3 minus? Chlorite. Nope. Nope. Okay, and for the sake of the recording, the suggestion was, well, it's chlorite because it doesn't have 4. Nope, that's wrong. Okay, fine, Mike, it must be chlorate because it has 4. Nope.
Chlorate is the 3 negative and perchlorate is the 4 negative.
Whoops. It's chlorate. What is the ClO4? Perchlorate. And so we run into this dilemma of what's more and less. That's a really challenging question, which ultimately means stop telling students that. Because the only reason the more and less work is because you've memorized the two things that were more and less. Well, if you were going to memorize it anyway, why the hell are you creating an arbitrary system of defining more and less? Okay? So this does add a wrinkle to it. So when we're talking about these, note with all of these systems or all of these names, we're talking about 8s and ites. I'm going to erase all that. So those 8s and ites are ways that we can differentiate the amount of oxygens associated with an individual other element. Okay? So that we know one has more oxygens or less oxygens in another system. Okay? But we would have to know what those states were. What we didn't address here would be the other common suffix that shows up. What's the other common suffix? Ide. The 8s, where we're looking at our T in the name, has to do with oxygen in our compound, or oxygen in the formula. When we switch to ide, we no longer have the T, and we now switch to the letter D. What does the letter D mean? Single element. The 8 and the ite, where oxygen is in the formula, and we have another element. Which, as you were suggesting, that means we have 2 plus, well, we'll stick with 2 elements at this point. Okay? Yeah, I'm going to just stick with 2 elements. The ide, with that D, is a big red flag that we're looking at a single element. So when we're processing out a name, if it says sulfide with that D in it, we know that all we're talking about is a sulfur atom. How many sulfur atoms is a problem for a different question. But we know sulfur's in our formula. Kind of make sense? Is that a yes, everybody? Yeah, it totally makes sense. Awesome, I love it.
Yes.
Cyanide. Close, but not quite. What's cyanide? Well, I see the ide with the D, right? Which means? Single element. What element is cyan? And because you did Unit 1 and you reviewed all the names of all the elements, right? You know that one, right? Cyan is clearly element number. I was looking for, is it C? No, it can't be C. That's carbon. It's element, not an element. It's 2 elements. It's Cn minus. But it has the D. Yeah, there's an exception. It's not iron. It's Cn minus. Cyanide is Cn minus. It is not a single element. It's a complex. I'm taking a carbon and a nitrogen. I've smashed them together. That makes cyanide. Okay? So in that statement of D means single element, is it true? Most of the time, but not all the time. Cyanide is an exception. Okay? But at least there's only one exception. What element is hydrox? It's not an element? No, it's not an element. That's 2 elements again. Okay? So when we're looking at our nomenclature systems, there are lots of things out there. There are lots of rules that we could start to put in and say, because I see this, it means this. I see this, it means this. As we saw with the 8s and the ites, was it true? No. It wasn't true at all. Okay? We were required to know more information to make this more and less make sense with the 8s and the ites. Okay? Talk about the ide versus the 8s. T versus D. D meant single element. No, it didn't. Okay? Which means what we're trying to do, or what I think happens as a field, is we try to come up with these rules so that we can tell people to memorize this rule so that you'll be right. Everyone goes, okay, I'm going to memorize the rule, and then you get something wrong because you followed the rule, and you go, well, stupid science has exceptions. This isn't stupid science has exceptions. This is stupid humans have exceptions. The name of a compound is not a universal truth. Humans came down and said, that's the name. And what we're trying to establish is a reason or a logic behind that to make it easier to discover those names. But ultimately, the name of your compound is entirely arbitrary. It is accepted fact. Just like you've already accepted the fact that when I say O, I mean element oxygen. So what does that mean you should go through and do when dealing with nomenclature and these complex ions? You need to memorize more things. Okay? There goes, oh God, that makes life miserable. Okay? It does make life a little bit more miserable to memorize some things, but memorizing things is a good thing. Okay? What is something that you generally like your instructors to do with regards to you?
Explain things.
Explain things. Know your name. Okay? That adds a whole nother layer of communication and a kind of collegiality by knowing your name. So it's insanely frustrating that I don't know most of your names. Well, I think I know most of them. Okay? Because if I can call you out by name, you're not like, dang, I can't disappear into the ether. He knows I'm here. He's watching me. I need to do better. Okay? It builds a better system. So we want to have that name, but ultimately it is arbitrary. I can't look at you and be like, oh, you have brown hair. That must mean you're Karen. That doesn't make any sense. Okay? But that's what we're attempting to do with general chemistry nomenclature. There are rule sets that we're supposed to follow to get to those names. Those rule sets are ultimately human defined. Someone just said they have brown hair, therefore their first name must begin with a K. Okay? Because they have brown eyes. I don't remember your color of your eyes. Brown eyes. Cool, I got it right. Okay? The next letter in their name must be an A. Okay? That's what we're doing with Gen Chem. So for you to go through and name a compound, you have to know the rules. That's all it is. You have to name it. You have to follow the rules that we have defined and accepted. Okay? And we attempt to come through things to make life easier. Okay? So that you can memorize some of those pieces. Okay? There's a mnemonic device that floated through the tutoring center probably 6 years ago about camels and phoenix and something else where if you count the number of vowels, it tells you the amount of oxygens, and the first letter told you that first. It was weird. Okay? People loved it. I still, to this day, don't have no clue. Okay? So what do I expect you to be able to do? Well, I expect you to be able to come up with those names, which means you have to memorize it. Memorize all the complex ions. Okay? And that's where everybody in the class should be like, no, you don't expect us to memorize all the ions, because I watched the video, and the video said I don't have to memorize them all. I only have to memorize these ones. 7. I can never remember if it's 6 or 7. Okay? So you should memorize those 7. Why should you memorize those 7? They're incredibly common. And not only are they incredibly common, they cover the common exceptions to the rule with element D. That's why you're told to memorize it, because it can help you navigate the system. So what happens when you encounter a complex ion or a thing that you've never heard of? Look it up. Look up what that ion is. Look up what its formula is. Look up what its charge is, which is going to become relevant. Once you have that minimal information, now process out the rest of the name. Okay? Use that as small steps to get you that information in that practice. Does that make sense? Questions? Okay. Oh, I should probably plug that in. So if we're now moving on to the next part, how do we go through and name? You ready to watch like gory detail? Is that a yes? Yeah? Okay. And of course we'd make approximations and simplifications as we go through and address these things. But I see a metal and a non-metal. How do I know that? Periodic table. I've followed along with the periodic table with those individual systems. I'm actually going to draw that underneath. Picked red for the metal. Yeah. Okay. Why would I put CN with an underlined T? Cool. Means something bigger. I would argue it means something complex. And as a complex non-metal system. Okay? Why do I go through and identify this information? Well, if I started off now with the very first one, I've got a metal and a non-metal, single elements of each. I know that compound is binary ionic. The next one, two nonmetals, I know that one's named based off the covalent rules. The next one, two nonmetals again, that's a covalent rule system. Last one, again ionic because I have the metal showing up. I have the complex one, so I'm looking at a ternary ionic. By classifying those systems, I've now centralized or compartmentalized the rule sets I'm going to have to go through and follow. Okay? Within those, if I'm now stuck on a test, what am I going to immediately do? Skip the hard ones. Which ones do I find easier? Okay? I personally find the covalent compounds really easy because everything's real straightforward, straight out of the formula and straight into the name. What do I mean? Well, N stands for nitrogen. So I'll write nitrogen. O stands for oxygen. Except, since it's the second one in the name, I'll switch it to oxide by dropping off the suffix. How many letters do I drop off that suffix? Enough that it sounds cool. Oxide sounds a lot better than oxyide or oxygide. Like that doesn't make any sense, so we just start lopping things up until it sounds reasonable. Okay. The next part, it says two nitrogens. The two is a subscript, applies to what is immediately in front of it. And what is immediately in front of it is that nitrogen. I want two nitrogens, I will call it dinitrogen. I'm using the Greek prefix to represent the number of those elements. Okay, I can move to my oxygen. I've got a 5 after it. That means I need 5 oxygens. I know my Greek prefix for 5 is, okay, penta. Pentoxide? I don't know which one sounds better. How can I dodge having to worry about teaching you which one sounds better? Multiple choice. Real easy. Okay? Now I don't have to worry. Because do I keep the A? Does anybody know?
Sure.
Oh, some people are like, no, you don't. I genuinely don't know. You don't? Okay, so cool. It's pentoxide. Now you learn something new. Same here. Okay? Not a huge issue. You're identifying those pieces and you've nailed that down. Okay, the next one I would move to is my carbon dioxide. Same process. Carbon symbol. I already actually specified some information. Carbon symbol, oxide. Okay, that suffix that changed it, ox, is going to reference oxygen. Go to my prefixes. That tri corresponds to the amount of carbons. And I know it corresponds to the amount of carbons because this is a covalent compound. That's the rule set you use with covalent compounds. What happens with the oxide? Well, I had a di in front of it. And I've got my formula, C3O2. Okay. Between the next two, binary ionic or ternary ionic, which one do I think is easier? Binary, because it has less things in it. Okay. It doesn't have to be fancy. Cr, what is Cr? Chromium. Do you know how to spell chromium? Oh, it was rhetorical, sort of. Okay. Multiple choice. Don't stress. Okay. So I know I've got chromium. Do I know what O is? Okay. Oxygen. Except I'm looking at the name for the compound. It's coming at the end. This one's consistent across all rules. Okay? Or all nomenclature classes. The second element, we always change the suffix. We change the suffix to "ide." Why do we do "ide" and not "ate" or "ite"? Single element. Okay? Cr2O3 isn't a complex ion that I had to have memorized. This is a new compound. How do I know it's not an ion? What is an ion? I got my eye on you. It's charged. How do you know it's charged or not charged? The upper right-hand corner goes all the way back to the atomic notation we talked about in our last unit. We look at the upper right-hand corner. There's no charge written there, which means this is not an ion, which means I avoid the 8s and 9s. Okay? Am I now done? Nope, because I have to remember an extra rule. With my binary ionic compounds, I have to specify extra information for the metal if what? If it is a metal that has more than one common ion charge. Is chromium one of the metals that has more than one? And that can be a really hard question because you look at the periodic table, which ones was I supposed to know, the ones that have it? Should I memorize the ones that didn't have it? You should memorize the ones that you're supposed to know. And if it's not that, what do you need? Now you need to specify the charge. Okay? So in memorizing the charges, which columns did we need to, or which things did we need to memorize the charge on?
1, 2.
Group 1 with what charge? +1. Group 2 with +2. What else do we have to memorize? The other side, we could go with nitrogen, oxygen, fluorine, but ultimately those I'm not going to stress about because those are all negatively charged. And when we're talking about our ionic compounds, the only thing we're specifying the charge on is the metal. So I don't care about those. So group 1, group 2, now what? Aluminum, which has what charge? +3. Zinc, +2. Cadmium, +2. Silver, +1. What charge do you think mercury would have if it had a charge? +2. Why do you think it should have a +2? In the same family, we would predict it to have a common charge of +2. Does it? Yeah, it also has a plus charge or a charge of +1, which is why we don't memorize it. Okay? So cool, with that information, chromium was not one of the elements I listed, which means I must specify the charge on the chromium in this compound. I will use parentheses right after the chromium, and I will include a Roman numeral to specify the charge. Looking at my formula, where is the charge for chromium specified? So one suggestion, it's found in the upper right. So what's the charge on the chromium then? We would say 0 because there's no charge written there. This is a compound. We're not specifying the charge on the individual atoms. We specify the charge for the compound. Okay? So the compound has a 0 charge. Does the chromium have a charge? It does. Now what becomes that charge? Okay? That charge is going to come from recognizing how the charge of all the other elements in that compound balance out to generate the overall charge. So chromium is going to come in with some kind of charge. So let's just use a symbol for chromium with a charge. But I have 2 chromiums, so it's going to be chromium plus chromium with its charges. Plus oxygen, because oxygen could come in with a charge. And I have 2 more oxygens. And then this will have to equal my overall charge. And now we can start with this formula to start to put information in as I have it. Before I even do that, I'm going to simplify it a little bit. How many times did chromium appear? So I can say 2 times my chromium plus 3 times my oxygen. This will equal my overall charge. Is the overall charge given to me? It is. That's the only thing given to me in the upper right-hand corner. And what is specified in the upper right-hand corner of the compound Cr2O3? Nothing is specified because the charge is 0. I can now try and go through and solve this. For people that have advanced far enough in mathematics, this is not an easy thing to solve. How many possible solutions are there? Infinite. Okay? One of those infinite is correct. You have one equation with two unknowns, that's not possible to solve definitely. Okay? So we need more information. You remember we said there were certain charges you needed to have memorized? Yeah? And we said we didn't worry about the nonmetals because when we were looking at the chromium, chromium was a metal. We didn't need to specify the charge on the nonmetals. Why did we not specify the charge on the nonmetals? Opposite of that statement. The nonmetals have a single charge. Are you responsible for knowing the charge on a nonmetal?
Yes.
Yeah. Everything under nitrogen is -3. Everything under oxygen? -2, which means the charge on the oxygen is a -2. I can modify my equation. 2 times the charge on the chromium plus 3 times the charge on the oxygen. The charge on the oxygen is a -2. This must then equal 0. I can now go through and just do algebra. 2 times the charge on my chromium will have to equal a +6. 3 times a -2 is a -6. I add 6 to both sides to get that to cancel. So 2 times the charge on the chromium equals 6. Divide both sides by 2, and I get 6 over 2 is my charge, also known as 3. So what do I do with that information? Roman numeral 1, 2, 3. That's where it comes from. Ta-da!
You always have to do add the Roman numeral if it's not balanced. If it's not like equal. Or
When do you need the Roman numeral?
if it's ionic.
You can use the Roman numeral when it's a binary ionic compound. You can use it also when it's ternary ionic, which means anytime you have an ionic compound, you should be asking yourself, should I use the Roman numeral? When should you use it?
Where's the charge on the metal?
Your metal will always be charged.
When there's multiple different.
When there's variable charges for the metal. Do you know which elements have variable charges? No, which means the way you figure it out is you've memorized those columns that we talked about. Group 1 was +1, group 2 was +2, aluminum +3, zinc, cadmium, and silver, okay, are also required to be memorized. None of those things that I just listed off include chromium, which means chromium, I must list it. Okay? A nice little whispered suggestion was put out there. If it's a transition metal, you must specify it. Where are your transition metals? The middle of the periodic table. That would be starting with scandium and ending with zinc. So if you use that cheat sheet, if it's a transition element, you specify the charge. You specify the charge on zinc. Should you do that? No, because zinc has one charge only. You do not specify it there. You're like, it's just more right information. Tough. That's not the rule. The rule is you provide only the information that is necessary to solve. Since everybody knows zinc is a +2, writing the Roman numeral for zinc is wrong. Which means if you memorize, transition elements just need the Roman numeral, there are 3 exceptions to your rule. Yay, exceptions. Don't blame me for your exceptions. I get mildly passionate when people start talking about, there's this thing. The tutoring center talks about transition element thing all the time. I hate it. Right? The majority of the time, you'd be right. Okay? I also know that the majority of people are listening to what the tutoring center, which means what questions typically show up on the test. Zinc, cadmium, and silver. You just shafted yourself. Okay? So cool, we now have our formula for chromium oxide. That only took a half an hour. Okay? Why is it taking a half an hour? just because it's a pain in the ass doesn't mean it takes forever. Okay? I can do lots of things that would be a pain in the ass that go real fast. How many times have you practiced it? Oh, you haven't? That's why it's so slow. Try practicing it. Try practicing it to recognize there's only a certain number of combinations that you could possibly encounter. And with that practice, you will build up a memory bank of things that allow you to solve much swifter. Okay? This process that we just wrote out here, people don't like. Okay? So other people invented rule sets. They invented something called the crossover method. More things for Mike to get angry. Okay? The problem with the crossover method is nobody uses it correctly. If you use it correctly, it's fine. The issue is you never use it correctly. And by never, that's a bit excessive. Should we show the crossover method? Is anybody excited? Well, oh, let's look at that. No? Okay, cool. Let's avoid that one. Okay? If you happen to know the crossover method, that's cool. We'll come back to it in a second, and you can test it on a new question. We got the dinitrogen pentoxide. We got the tricarbon dioxide, which then means we're left with the lead-4 acetate. Lead is a metal, which then means I'm going to have to be concerned about the charge. Thankfully, it's given me the name, so I actually know the charge. Lead, the symbol for lead is Pb, and I know that because I memorized it. The charge on lead is... This is where it goes, oh, I don't know what the charge is on lead. It's not something I was forced to memorize. That's true. You weren't forced to memorize it, which means we told you. That's the Roman numeral. The charge on lead is +4. I will always specify the sign. I'll always add that +4 in front of it, that plus. Okay? So then we move to acetate. It's a T, so I know it involves multiple atoms. Which multiple atoms?
C2H3O2.
Okay? C2H3O2. Okay, I'm going to come back to that in a second. How do we know it's C3H2? Well, I already forgot the formula. C2H3O2.
Memorized.
You memorized it. Why did you memorize it? Because you watched the lecture and I told you, you need to memorize this. That's why. Why am I telling you to memorize it? Where have you seen acetate before? I've never seen acetate before in my life. Anybody had a salad? I don't know, within the last couple weeks? Yeah? What'd you put on that salad? Dressing. Guess what's in that dressing? Acetate. Okay? Acetic acid, vinegar from your dressing is going in. Acetate you've been exposed to multiple times over. Okay? So it's C2H3O2. What I'm trying to do is now balance the charges on this, which then means it's not just knowing the formula C2H3O2, it's also knowing the charge on that acetate. What is the charge on that acetate? It's a -1. This is another case where I would put the number in so I'm extra clear with that sign. Not a question. Okay? I have to make sure that when I put this formula together, what's the overall charge? 0. Which means I now have to consider taking a lead of +4 and an acetate of a -1 and finding how to combine them. Right? Which we let's say Wednesday, right? We talked a little bit about that on Monday. We want those charges to balance out. That's our rule. They need to balance. So what's the lowest common multiple between 4 and 1? 4. How do I make a 4 into a 4? Multiply by 1, which means I have 1 lead. How do I make a 1 into a 4? Multiply by 4. Let's backtrack that out a little bit. I just need 4, right? So is this now a good formula? PbC2H3O24. Right? Because it's not O24. What is the 4? It's to reference acetate. What is acetate? C2H3O2, which is why we include the parentheses around that to be extra clear that that's not doing a 24. It's now 4 of whatever's the parenthesis. So let's push on that. How many oxygens are there? If you think you have the answer, keep your mouth shut. If you don't think you have the answer, now you can answer. Like, that doesn't make sense. I know. I didn't think through it all the way. All right. Each acetate gives you 2 oxygens. I have 4 acetates, which means 8. So it becomes a multiplier in it. Is that going to become important? Did you watch all the lectures for this week about like balancing chemical equations? Yeah? Yeah, there it is. Yep, it's going to become important. We have to deal with how that multiplies through. Okay? So we now have our proper formula. If we write PB1, parentheses C2H3O2, and parentheses 4, are we going to be correct?
No.
Run into a little bit of a gray area here, but I would argue you're probably going to have people take off points and say you're not right. Why are you wrong? It's a stupid rule. The 1 wasn't necessary. Because it wasn't necessary, you added extra information, therefore you are wrong. It needs to be PB without the 1. Okay? If we want to get fancy, we could get fancy and we could box in our answers. Okay? I will see students go through, and we'll point this one out. If you'll note for the lead, I did see your hand, give me a second. For the lead, we've got a 4 written underneath. Is that typically where we write our charge? No, we typically write it in the upper right-hand corner. Why do I not write it up here? It gets confused within the answer. Will I understand what you're trying to write, particularly for paper homework? Yeah, I don't care. Okay? But if you move into a different class and you show that notation, that's technically wrong. Okay? And you shouldn't do that. Does that make sense? Okay? That's why I've shifted and dropped my charges underneath so that I can also have that space to run a calculation if I feel I needed to run a calculation. Yes, Eden.
So can you explain why the 4 is on the outside of, like, one more time?
Why it's on the outside?
Yeah, because I know the P or the lead charge is 4, and but the charge on acetate, that's only 1.
Minus 1.
Minus.
Sorry, I
Okay.
needed to make that a 4. What I think you're actually asking is what's getting confused and where these numbers are placed. When I place a number in the upper right-hand corner, what does it mean? Charge. How do I write the name of a compound that has a charge? Roman numerals next to the name. So where I transfer that information for each of the individual notations matters. What does this 4 that I've written outside the acetate mean?
Yeah, how do you know the acetate is only
I'll answer that question next. What is the point of this 4? What does it mean? There are 4 acetates. It does not mean lead has a +4 charge. That 4 means I have 4 acetates. Why do I need 4 and not 2 or 6 or 20? That's to balance the charge of the lead. But that number down there is only talking about how many acetates are present. Okay? I can change lead to be something else. That number is going to change. Why? Because the 4 changes the amount, which changes the charge contribution from that molecule into the whole system. That charge contribution is what we wrote in the upper right. That was all that nasty work. Kind of, sort of? The next question you followed up with was, what is the charge of acetate? Is it a -4? No. Acetate is not a -4. What is the charge on acetate? -1. How do I know the charge on acetate is -1? And this is where we look at the periodic table. It's not on the periodic table. It's in your brain because you memorized it. That is one of the ones that you should have memorized because you will see it frequently. Again, you've used it, you've ingested it. You should have that memorized. Does that make sense?
The charge and the name.
The charge, the name, and, depending on how you want to reference it, the symbol. Okay? In this case, a chemical formula. And in that chemical formula, it's not just that it's carbon, hydrogen, and oxygen, it's the exact amount of each of them too. You change that amount, you change the compound. Yeah? I'm going to do something I'm going to regret. I mean, I always do something I regret. It's part of existence. Oh. It's just going to cause a mild, retching. Crossover method. I take the subscript and I make it the charge of the chromium. Oh, and I think I even heard someone say, yes. Open a can of worms. Okay? You say, well, isn't that what we said the answer was? Didn't we say the charge on chromium was a +3? Cool. There was another question that I drew up, right? What's the name of this compound? So that's manganese. We have our oxide. Is manganese an element we're required to have the charge memorized on?
No.
Nope. So that means we have to specify it. And because Mike just showed me this awesome crossover method, the charge on that manganese must be a 2. And you're wrong. What is the charge on the manganese? It's a +4. There's 2 oxygens with a -2 charge. There's 1 manganese with an unknown charge. What must this overall equal? 0. X minus 4 equals 0. X equals +4. That's my charge on the manganese. Right? The crossover has issues, and they're easily exploited issues. Right? So if you're going to choose to use that, I really caution you against it. Okay? Because you've chosen to take, you were forced into, because of your schedule, to take a class with me, one of the things that you may or may not benefit from is that I've been the collector of all sorts of crap that comes together to deal with exams. And one of those things is looking through exam data, particularly for the final exam. In the final exam, we have a question about nomenclature. About 80 to 90% of my class gets that question right. About 10 to 20% of every other section gets that question right. And you know why? Everybody else loves the fucking crossover method. And they've taught students that that's the appropriate way to do it, and what quickly turns out is it ain't. It does not work consistently. My whole job, if you're looking at why are you showing all this work, Mike? I can do that in my head. The point of me showing all that work isn't for you doing it in your head. It's for that person that can't. And I'm showing all that work to improve consistency of your result. And if you doing it in your head gets you a consistent result of 50%, I'm not happy with that. So I'm going to tell you to write out your work. Because what have I found? When you write out your work, the consistency goes up to 70 to 80%. That's why I push it. The algebra process that we just walked through takes someone's consistency for getting the balancing of dealing with a name from 60% up to 90%. Where do you want to be? I genuinely don't know where you want to be, but I'll tell you where I want you to be, up in that 90% range. So I'm going to do everything I can to put you there, but you also have to take that advice in hand, as painful as it is. Kind of, sort of? Questions? What time is it? When are we done? 45. 45. Yes?
For the example that we did for like the cyanide.
You mean all the stuff I erased?
The hydroxide, sorry, where you had like OH with the negative on top. Like how do you know when to put the hydrogen in the front of the element list versus, if you get what I'm saying?
If we look at that top one, we've got carbon, hydrogen, then oxygen, then we have the charge. Upper right-hand corner. We look at hydroxide. It was O first, then hydrogen, then the negative charge. Why? Does this provide the same information? Yeah, it does. Formulas, as we discussed when we looked at Lewis structure, don't give us structure. The structure comes from manipulating the formula to draw out a larger thing with other rule sets in mind. So the formula ultimately could be written any different way. I could even write the formula if I really, really wanted to. Oh, actually. Sorry, it's not a -2. Just saw that. CH3CO2 minus.
Doesn't it change the reactions though?
The only reason it would change the reactions is if it changed the structure. Does the formula tell you structure? It doesn't. So which formula system should you use? Depends on the context of the situation you work in. Okay? Universally, you'll find everybody tells you that that's the wrong way to present that one. That one, no one will like that formula. Okay? Why? Some student asked me this, and I was like, I have no idea why, but I know that's wrong. And then I asked a whole bunch of chemists, why is that wrong? And they were like, I don't know why it's wrong. I was like, you got to be kidding me. No one knows why that's wrong? And I looked it up. Guess what it is? I think it's called Hall rule or Hall organization. Someone some time ago went through and said, this is the order that you list elements in a formula. It was just established. And because it was established, everybody just accepted it. And since it was only written C2H3O2 and never H3C2O2, we just know it was wrong. There's lots of things like that. You can look at English things about English language stuff. Okay? The big black bear versus the black big bear. I didn't like the way one of those sounded. Yeah, that's because in the English language, there's a proper order in which you place those. And as soon as you place them out of order, English speakers will go, why'd you do that? Like, all I did was switch the two adjectives around. What's wrong with you? Okay? But there's a proper order in which you do it. That's what's going on within this formula system. So why does it switch? It switches depending on the context. If we look at the far left one, why do you go to the far left one? Well, if we actually draw out the Lewis structure for this compound, why would I choose that formula? That formula starts to give me some structural information, which could change my chemical reaction. Why do we use the red one? We decided the red one didn't give structural information, and it's a simplified version. So why do we make you look at the simplified version? Come on, you know the answer to that. Okay? You don't want to look at the complex version yet. So we'll give you the simplified stuff first, and then we'll build outwards. All right? So it's really just an accepted notation. Anyway, it feels better to say O than ho when you're talking about formulas. I kind of get in trouble with that. Maybe I shouldn't have recorded that. Okay, make sense? Next question. How hard is nomenclature? Wicked hard. Right? Guess what? Wicked hard is what you're saying right now. And I would bet in 3 weeks, 2 weeks, 2-ish weeks, when the exam week rolls around, the week right before spring break, you're going to be like, please, Mike, just make the whole exam nomenclature. I don't want anything else. Just give me nomenclature, and you would ace the bejesus out of it. Okay? Because nomenclature requires understanding the rules. Once you know the rules, as straightforward. But you have to get past that wall. Okay? If we can look at like the time spent learning. So time and like knowledge. Let's try something like this. It's a fun graph sometimes. Okay, you'll look at nomenclature and be like, I'm spending all this time, but I'm not gaining any knowledge. But then this happens. And you're like a master. And everybody's flipping out because you're down here right now. Okay, what is that time span? 24 hours, maybe, of time, at most. You ready for the curve for OChem? Okay, bio. That's my opinion of bio. It's not the nicest, but I'll leave you to extrapolate what that means. Okay. Everything's different for different reasons. Okay? Other questions? You give me freedom, you can get all sorts of weird stuff. Why do I hate on bio? Because I wasn't good at it. Okay? I wasn't good at it, but not because I didn't try. I wasn't good at bio because I felt all I had to do was memorize a bunch of facts. Why do I want to memorize a bunch of facts? What can I do with that fact? What can I do with acetate? With acetate, I can now run a chemical reaction. If I understand what the formula is for acetate and its structure, I can predict how it can transfer a hydrogen from one thing to another. Why would it transfer that hydrogen? That now gives me information that, believe it or not, I could feed back into bio and explain what's going on in bio. And that why did it happen in bio isn't a bio explanation. Guess what it is? It's a chemistry explanation. So bio kept saying memorize, 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 and then chemistry was like, this is why you're doing all of this. It's like, oh, well, I think I like that better. Okay, personally. Okay. That said, again, just because I hate on bio doesn't mean it's not important. Bio is still very, very important. It's also just not my cup of tea.
We have next Monday off.
We do indeed.
Okay.
Next Monday is a holiday. So, I mean, you can show up to class. Security will chase you off. None of the doors will be locked or unlocked. They should be locked. I don't trust security on that. They could be unlocked. I shouldn't have recorded that either. They're not going to listen to me. It's fine.
Can I get like a little, I was kind of confused on the balancing chemical equation.
Sure. Because I know students hate this. So we'll go ahead and do it. So when we're talking about balancing a chemical equation, we need to look at a chemical equation. So I'm going to look at the chemical equation where I react hydrogen gas with oxygen gas to produce water. It's also one of the reasons why I don't like teaching general chemistry. Note, I said hydrogen gas and oxygen gas. Does my equation say that?
Not yet.
No, it doesn't. Should you have that phase information in there? Yeah, you should. Okay? Depending on where you're at or what context of what you're trying to do, you may drop it off. It's up to you. I would argue in this case we care about balancing. What is balancing talking about? The coefficient in front. Since it's the coefficient in front, I don't care what's happening about the phase. That's not relevant to my discussion. I'll typically drop the phase off. Right? So when we're looking at balancing, what you're trying to ensure is that you do not create or destroy matter. All right? That's kind of the bottom line. So when we look at this left and right, this is an equality. The left side must equal the right side. Right? So if I look at the left side, how many hydrogens do I see? 2. So my notation is I go right underneath the reaction arrow and I would write the element symbol that I'm looking at, and I'm just looking at the element itself. I see 2 hydrogens. I see 2 hydrogens because I have that subscript right before the element H. That 2 is what's corresponding to it. And I look at the right-hand side of the equation. How many hydrogens do I have? Again, 2. So if I'm looking at balancing, my hydrogens are balanced. Left and right, I have the exact same number on both sides of the equation. Everything's dandy. Right? Now I would move to the next element, my oxygen. Well, how many oxygens do I have on the left? 2. Same process, the coefficient applying forwards. How many oxygens do I have on the right? 1. Right? There's actually a couple ways that we could potentially logisticize how we could look at this. Right? If we look at this as a recipe, right? You open up a bag of chocolate chip cookie or chocolate chips to make your cookies, right? Right? Did you have leftover chocolate chips? Yeah, that would just be left over in the process. So could we theoretically do that with a chemical equation? Yeah, we could go through and say, well, plus, there's an oxygen atom left over. It didn't make it into the water molecule, and now it would be 2. Don't write that down. It looked like most people weren't, but there were a couple people drawing. Okay? We could theoretically go through and make that statement. Okay? But the issue that we encounter with that is that we're now saying we form an oxygen atom, chilling off on its own. That doesn't happen. Okay? So if I'm trying to represent what's chemically happening in my system, at no point can I grab the oxygen atom at the end of the experiment and be like, oh, this was what was left over. It doesn't. Okay? It doesn't happen. Which means drawing my equation to balance it this way doesn't make physical sense. Okay? So I can't just list the remaining pieces that didn't react. So that has to disappear. Okay? So I have to come up with another way to ensure the oxygens are balanced on both sides of the equation. Okay? There's technically 2 ways to approach this. Should we look at the right way or the wrong way first? The right way. Okay? The right way. I need to make sure that I have 2 oxygens on the product side. Okay? And I know I said right way first. I'm actually going to make it wrong. I apologize. Sorry, Lena, because you told me to do the right way. Okay? I can go through and say, well, now I have 2 oxygens, right? I put the 2 next to the oxygen. That's now 2 oxygens. Is that the same chemical expression now? No. Instead of forming water, I've now formed hydrogen peroxide. Those are very different substances. So when I'm going through to balance the equation, I cannot change the subscripts. Those subscripts are locked in place. Those are what identify the species that I'm working with. So if I need 2 oxygens, there's only one place I can put that 2. That's an eraser. That's in front of that entire part of my expression. That 2, similar to the parentheses, will apply to everything after it up to a mathematical operation. So what do I mean by that? That 2 is going to apply, come on, pen, to the hydrogen. It's also going to apply to the oxygen. It's not going to apply any further because there's nothing else out there. If there was, say, another thing out here, just put Bob out here because he's a nice guy, okay? That 2 isn't going to apply to Bob because that's a mathematical operation. Okay? So that part is invalid. Kind of, sort of? So that 2, because of the value of where we've put it, now applies to everything after. I now have how many oxygens? I now have 2. I have the initial water molecule, but now I'm saying I have 2 water molecules. If we were to draw this out, kind of not formulaically, we could write it out as H2O, H2O. That's what that 2 is now meaning. Okay, on the other side, I have H2 and I have O2. Kind of, sort of? Okay, so now I've balanced the oxygen. But is it balanced?
No, is it now?
As soon as I add a coefficient, there's a potential that I have goofed the balancing of something else all the way at the beginning. So as soon as I change a coefficient, I now must double back through the entire process. So I will go back up to my hydrogen, and I'll check my hydrogen again. On the left-hand side, how many hydrogens do I have? 2. And on the right-hand side?
4.
Because I've written it out this way, we can see that a little bit better. I have 4, which means my hydrogen is not balanced. How do I balance the hydrogen?
Add the 2.
I now need a 2 over here. Okay, I changed the coefficient, so maybe I got to stress about the oxygen. Okay, Nami. What I would go through and do is now also check the oxygen. Okay, for me personally, I would switch that to, again, I'm using the arrows because I'm showing that I've changed it. I've put the work down to explain that. Now I go back and look at the oxygen. How many oxygens do I have on the left? 2. How many oxygens on the right? 2. Okay. My preference, I changed another number, so what should I do? Check it again. So I'll double back to hydrogen and say, how many hydrogens do I have on the left? 4, and I'll change that 2 that I wrote to a 4 because I goofed that number in. All right. How many on the right? 4 left for oxygen, 2 and right, 2. Now what do? I always say, oh, now it's balanced. I would argue at this point what you should do is check it again. And you should check it again. And this is what's presented in the video. You should continue to check it until you're like, dude, this is so stupid, Mike. Why are you making me check it this many freaking times? Because it's not changing. Yep, once you reach that point, now you can stop. You've built a little bit of tension and anger. Great, it's now sticking in your brain. You'll remember it. And now you can move on. Okay? So we could now say, well, the equation is balanced. How do I ask a question about it? Okay, neutral, that would be implying charges. Did we talk about any charges anywhere? Nope. And in fact, if we look at the upper right-hand corner, it was neutral no matter what number we put as coefficients. So it doesn't have anything to do with neutrality. Okay. Did you balance it correctly? I could ask for what's the sum of the coefficients. So now take that purple number underlined in front of each of those and add it all up. When you've added it all up, that's now the sum of the coefficients, and I can check that you've correctly balanced it that way. I could say, what's the coefficient in front of water in the balanced equation? Okay. What's the sum of the coefficients on the reactant side? What's the coefficient in front of oxygen? There's so many different ways that I can ask, what are those numbers? Does that make sense? Ish?
For the sum, would you include 1 for the oxygen on the left?
Cool. What is the sum of the coefficients, of all the coefficients? Okay. I have a 2, and I have a 2, which means 5. There's an implied 1. Do I need to include that 1? Yeah, because it's not 0. If it was 0, there would be no oxygen. Okay? So you will have to include that 1, which is why some people will include a 1 there. Okay? When you're balancing, it's your work. You put whatever you want there that balances the question. Okay? New question. I can do math. Can I do math? Is it still balanced? Did I do math? Cool. Yeah, it's still balanced. Is this now correct? No. Okay? Which kind of doubles back to nomenclature. It's the rule for when we establish that we're balanced. Okay? Our rule is that the coefficients in front must be the smallest whole number possible. So if you balance it and get 424, that's okay. Officially, none of this work aligns, right? So don't evaluate it based off of that. But if your work somehow got you to 424, you should recognize that all of those have 2 in common. So you could divide everything by 2, get the 2, get the 1, and get the other 2. So when you balance, you must have the lowest whole number value. Right? Balancing, just like nomenclature takes a little bit more practice, but I would argue it's less arbitrary made-up rules, and it's more just do the things appear. Right? So I think balancing is one of the easier things because you will know when you did it right. When you did it wrong, you loop, and you're constantly changing numbers. That's because you screwed something up. Okay? With that, popular demand, we're done.